Hello students, welcome back. So now let us discuss the next topic of the chapter, that is vapor pressure of liquid solutions. As in my previous video we discussed in details about the vapor pressure, that what is the meaning of a vapor pressure and how it is measured. So now next topic is vapor pressure of the liquid solutions. You are also very much familiar about the meaning of the liquid solutions, where we have solvent in the liquid form always, and solute can be in the gas, liquid or the solid form. In the previous video also we discussed the solutions of the gases in liquids, about which the Henry's law that gave the quantitative relationship between the mole fraction of gas dissolved and its partial pressure. So whatever the things were there related to Henry's law, its definition, its mathematical expression, that we discussed in the previous video. Now we will discuss about the solutions of liquid in liquids. Mean to say, now the solute will be in the liquid form and also the solute will be in the solid form. Both these two types of solutions, they are studied under Raoult's law. So first of all we will take the solution of liquid in liquid, or you can say liquid solution. So here this is the Raoult's law for liquid solutions. It means now both the liquids, means component 1 and the component 2, both are in the liquid form and both are the volatile solutions, means both components they contribute in the vapors also. So now according to the Raoult's law, that states that for a solution of a volatile liquids, the partial vapor pressure of each component in the solution is directly proportional to its mole fraction. So it gives us the relationship between the mole fraction of any of the component and it's the partial pressure. So let us have the XI, that is the mole fraction of component 1, and P1 is the partial pressure of component 1. So according to Raoult's law, the partial pressure of component 1, that is directly proportional to its mole fraction. So same here for component 2. Let's have X2 is the mole fraction of the component 2 and P2 is the vapor pressure of component 2. So here I have denoted with green color component 1 and with red color the component 2. So P total, that is the total vapor pressure of the components to both the components, that is exerted. So now see, this is in the liquid form. So this is in the liquid, both the components are present, and red one is component 2, green one is component 1, and you can see their vapors are also present in the vapor phase. Now this is the vapor phase, and in the vapor phase component 1 is, vapors of component 1 is also there and vapors of component 2 is also there. So whatever total pressure that exerted by both of these components, that is the total vapor pressure. So this is according to Raoult's law. P1, partial pressure of any component 1 which is also volatile in nature, it is directly proportional to its mole fraction, and same way the P2, which is the partial pressure of component 2, and X2 is the mole fraction of component 2, and P2 is directly proportional to the X2, which is the mole fraction of component 2. So now the next, let us elaborate the expression further. For component 1, P1 is directly proportional to X1. Now for proportionality constant, if we remove this, we are applying this constant, that is the vapor pressure of a pure component. So this is P1 नोट. P1 नोट means जब वो अकेला ही component present है अपनी pure form में, और वो कितने vapors का pressure, वो कितना vapor pressure वो exert कर रहा है, जो कि हमने last video में भी इसको detail में समझा था. So that's why this remains constant for a particular liquid. So P1 is equal to P1 naught X1, and same for the component 2, P2 P naught 2 which is the vapor pressure of the pure component when no any other component is dissolved in this. So whenever it is in the pure form, how much vapor pressure that is exerted by this component, this will become the pure vapor pressure for the pure component. So P2 is equal to P naught to X2. Now according to Dalton's law of partial pressure, P total. So total pressure exerted by, according to Dalton's law, that is the total pressure exerted over the solution phase, that will be the sum of the partial pressure of all the components. So here we are having only two components, so it will be the sum of the partial pressure of component 1 and component 2. Same way, now we are having this P1 plus P2. If we substitute the value of P1, this one, and for P2, this one, so what we will get, the P total is equal to P1 naught, we have substituted the value of P1, and P naught 2, we have substituted the value for P2. So that is P1 naught X1 plus P naught 2 X2. Now further, X1, we know that the sum of all the mole fractions, that is always unity. So here we are having two components only. So X1 plus X2, mole fraction of the two components, that will be equal to 1. So X1 is equal to 1 minus X2. If we substitute this value X1 in place of this, we are writing 1 minus X2. And by solving this, the overall expression, we will get P total is equal to P1. So here will be P1 naught minus P2 naught minus P1 naught X2. So here what is the meaning? Now P total, the total vapor pressure over the solution phase, that can be described, or you can say that is dependent upon the mole fraction, or can be explained in terms of mole fraction of only one of the component. So here we substituted the value for X1. So in the final expression, here we are getting X2. So if we substitute the value for X2, and definitely we will get X1. So anyone, so we are not specifying that only that can be explained only in the form of second mole fraction of second component or the solute component. No, it can be explained in terms of the mole fraction of any one of the component. So further, diagrammatically, if we explain this thing, let's have this diagram. So here, see this thing, at this point we are showing that this is the component 1, where the mole fraction of the component is 1, and this side, when mole fraction of component 1 is whole, the pure component is there, its mole fraction definitely will be 1, and this side mole fraction will be 0, and this side X2 will be 0. So this side, what will be the component composition? X1 is equal to 1 and X2 is equal to 0. Slowly what we will do, the mole fraction of X2 will be decreased, and slowly mole fraction of X2 is increased. So by the end we will get this composition where X1 is equal to 0 and X2 is equal to 1. So now here you are getting the pure component 1, and here you are getting the pure component 2. So this line shows the vapor pressure. So if here is we are having the pure component 1, so this suppose let's have the vapor pressure of component 1 here, that is P1 naught. So this is of course the vapor pressure for the pure component, because we are having X1 is equal to 1 only here, only one component, where second component is 0. Mole fraction of second component is 0. Same here, by changing the compositions, by decreasing the composition of component 1 and increasing the composition of 2, mole fraction of second component, here we are getting the mole fraction of component 1 only. So this pure mole fraction of component 1 means we are having pure component here, and its vapor pressure, let's point out here, that is P naught 0. It is not like that all the time you are supposed to put the point of P1 naught here and P2 naught above this. It is the only condition when we consider that component 1 is less volatile. Component 1 is less volatile means pressure, or you can say pressure, vapor pressure of component will be less as compared to the vapor pressure of component 2. So this, if this is the condition, then of course the vapor pressure point of second component will be higher than that of the vapor pressure point of the one component. If we consider the reverse condition where P2 is less than that the P1, then of course the P2 node point will be here and P1 node point will be above than that of P2 node. So this was the graph which was showing. So this, if we join these 2 points, this will give us the P total. It means here in between these two, whatever composition that is changing, according to that vapor pressure is also changing, but the total vapor pressure that will be between this P1 node or P2 node. So here if we see this line, the mole fraction of component 1 is decreasing and component 2 is increasing. So that's why the straight line graph is here, and where x2 becomes 1, it touches the P node 2, and same for this thing. This side, by moving from this point, x1 composition mole fraction of one component that is increasing and mole fraction of second component that is decreasing, and at the end when mole fraction of one component that reaches to unity and mole fraction of second component that becomes 0, it touches the P1 node point, means vapor pressure for the pure component. So what is the conclusion we have drawn from this Raoult's law? That P total can be related to the mole fraction any one component. So see, I have written this expression again, that P total can be related to the mole fraction of any one of the component. Here previously I told you that here it is x2, it can be x1 if we put the value of x2 over there. And same way, generalized thing we have written here, that it is related to the mole fraction of any one of the component. Then P total varies linearly with the mole fraction of component 2. See again, if we say this thing, expression P1 node is constant, P2 node is constant, P1 node is constant, this whole term is constant. So that's why we can say that P total that linearly relates with the composition, or we can say the mole fraction of component 2. Then depending on the vapor pressure of the pure components, P total over the solution decreases or increases with the mole fraction 1, or increase of the mole fraction 1. So as already I told you that from the graph, that value of the P total that increases or decreases with the increase of mole fraction 1. So next is the composition in the vapor phase. Suppose this thing to be discussed about previously, whatever the composition of component 1 and component 2 there in the solution. Now what is their mole fraction in the vapor phase? Component 1 और 2 के वेपर्स, दोनों के वेपर्स अगर वेपर फेस में प्रेजेंट हैं तो यहाँ भी तो कोई उनकी मोल फ्रैक्शन होगी. सो उसको हम y1 और y2 से डिनोट करते हैं. सो लेट्स हैव y1 दैट इज द मोल फ्रैक्शन ऑफ कंपोनेंट 1 in the vapor phase, and this is y2 is the mole fraction of component 2 in vapor phase. Previously we discussed about x1 and x2. We used to write that compositions, so that compositions they were there in the solution form. Now we are talking about the vapor phase. So what is the composition of component 1 and 2 in the vapor phase? So that is written by y1 and y2. So by using again Dalton's law, P1, that is the partial pressure of component 1, is equal to Y1 or P total. P total will be constant. P total will be constant. Whatever increase or decrease in the compositions will be there, but the P total will, for the both the components, that P total will remain constant. So P1 is equal to Y1 P total. P2 is equal to Y2 P total. So here, by using this relationship, we can calculate the composition of or you can say the mole fraction of any of the component in the vapor phase. So this is all about the Raoult's law.